All right, let's go over these 12 days of statistics. So here we go. It's going to mix everything all together. So we have in this first one, we are told that we have independent events. And that's important. That's a very important fact because what that tells us is that we can just multiply those two probabilities together. And the fact that one thing happens hasn't changed the other. So therefore, I can just multiply the probability of a partridge times the probability of a pear tree. So the probability I'm going to get a partridge and a pear tree is 0.4408. Okay, next we have this find the probability of at least one female turtle dove amongst the two turtle doves. So, what is happening is we have this binomial distribution because since it's out of two, we know we've got a set n. So, I could call this a binomial. Um, so I could use the binomial formula, but we did learn at least one with a different technique. And so the probability of at least one is 1 minus the probability of none. So the probability that neither of the pair is a female. So that means 1 minus the probability they are both males. And so there you go on that. Okay, and then this next one, we have our 3 French hens. And so the probability that the hens have a French citizenship is 0.81. So we've got, we want to know a probability of exactly 2 out of the 3 French hens, or the 3 hens. Okay, so we have 2 French ones out of the 3. Because it's a set number n, it is a binomial distribution. So I want probability of exactly 2. Here's the formula, the 3 combinations of 2, the French probability squared, and then one of the not French. There we have that. So here's how I put it in my calculator. It's in exactly this or exactly that. PDF is what you do. And so there is how we calculated that. Okay, so this one's interesting. It has this thing that sounds kind of strange. There is an infinite number of calling birds. Well, what that is really telling us is that there's not a set number in this trial. We could go on forever, okay? So if there's not a set number in this trial, okay, and the probability of a bird actually being a calling bird is 0.63, what's the probability that the first calling bird is on the third attempt? Okay, so here we have so this is a geometric because we do not have a set n. And so the probability that we get the success on the third trial is 2 failures and then that success, which you can multiply out that way, or you could do geometric PDF of 0.63 on the third trial. All right, and the 5 golden rings. So the probability to get a real golden ring, okay, not just a fake one that's going to turn your finger green, a real golden ring is 0.72. So find the probability of getting 3 or fewer of those 5. Set n equals 5, so we have a binomial distribution, and so we want to get less than or equal to 3. So the work we're going to show is our first in the sequence, which is 0 successes, plus dot, 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 plus up to 3 in this series, which is 3 successes and 2 failures. Now, our calculator will accumulate from the bottom. So I can do binomial CDF of out of the 5.72 up to and including the 3. Up to and including the 3. So that's 0.4303. And the 6th day of Christmas, we want an authentic laying goose, and that's 83% chance of that. Now, there's an unlimited number of these geese. Okay, so that's no set numbers of trials. So we have a geometric distribution. So find the probability that we get a laying goose on or before the 4th. Now, that means the success occurs on the first success. The first success occurs on the first, or on the second, or on the third, or on the 4th. So this is an accumulation of geometric situations. So here I have a probability that x is less than or equal to 4. It says on or before the fourth, so equal to the fourth. So here's the work I show. I show a success on the first trial, plus dot, 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 plus a success on the fourth trial, which means I had 3 failures and then that success. So I geometric CDF that, and I want that 0.87 to be up to and including the fourth trial. And so there's how you do that probability. And the seventh day of Christmas, we got the 7 swans a swimming, but we have some swans that could drown. And so that's a 23% chance of that, which, whoa, that seems kind of high. So find the probability of exactly 4 out of those 7 swans a swimming. So find the probability that 4 of those 7 are drowning. Because we have this set number of n, it is a binomial distribution. So here I want exactly 4. So that's a PDF. 7 with 4 successes, so 0.23 to the fourth, and then that meant there were 3 failures. Calculator-wise, that went binomial PDF, 7.23, exactly 4 successes. All right, the 8th day of Christmas, we got sour maids of milking. We've got 8 maids of milking, but what proportion are we expecting to be sour? So find the expected number. Remember that expected number is the mean. Expected number is the mean. Geometric 1 over p, binomial n times p, which those come from your formula chart. In fact, I could pull that up really quickly to show you, because you need to be aware of where those formulas are on your formula chart. It's going to be right here in this probability section, and it's the binomial. So that one said, how many do you expect out of the 8? So see, we had a set n that was a binomial. So here's the average. Then this would be the standard deviation of that. But if we had geometric, how many do you expect to go until you get a success? That would be our 1 out of p, and with that standard deviation. All right, so back to this. So we just did our n times p, and that gave us our 3.04 sour maids of milking on average. So out of sections, groups of 8, we're going to get 3.04 of them on average. Okay. Find the 9th day of Christmas. We want the 9 ladies dancing, but they don't all accept an invitation. So we want apparently only 18% accept the invitation. Find the expected number of ladies you have to ask before one accepts that invitation. So that's our going until we have a first success, and it's the expected number is the mean. Expected number is the mean. Geometric 1 over p, binomial n times p. So there we have that. And so that's 1 over 0.18, 5.56 ladies accept you expect to ask that many ladies on average before you get one who accepts your invitation. Okay. We got lame leaping lords. 24% of them are lame. So now there's an unlimited number, meaning we don't say just out of 6, okay? So we are going until forever. There's an infinite many of these things. Geometric, not a set number n. So since we do not have a set number n, we want to go probability that x is greater than 6. Now, this is very interesting how we do this, because we want to know that the first one that you come to is after the 6th. After the 6th means the first one that we get is the 7th or past that. There's 2 ways you can think of this. If the first one you get is the 7th or past, then you don't care what's happening past the 6th. You don't care what's happening 7 and on. You are just specifying and identifying that the first 6 are definitely not a lame leaping lord. So in order to get that probability that it is greater than 6, that's 7 and on, I need those first 6 to be failures. So that's this. Now, you could also think of it like this. I want successes in all the places. I want all the places, but I don't want success amongst the first 6. I don't want that first success to be in the first 6. So a success among the first success being in the first 6 is geometric CDF of a lame lord in the first 6. So you could do everything minus the first success being in the first 6. And that comes out the same. So it just depends on how's your brain thinking of this, and people can think of it 2 different ways. All right, and that was the 10th day of Christmas, but we have now the 11th day of Christmas. So we have frozen pipes. Well, that's a problem if we want pipers piping. And so we need 11 pipers piping. What's the probability of a frozen pipe being 63%? Wow. We want 8 or more of those 11 are frozen. So that is greater than or equal to 8. We have a set number in. So we have the binomial distribution. So 11, choose 8, part of the sequence, plus dot, 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 plus 11, choose 11. So there is our work that we show, which we know that on our calculator, we do something different to come up with the answer. So remember, I always kind of write out my sequencing so I can visualize what I need. So I know exactly what I need to take off. So here's the sequencing from 0 successes up to 11 successes, okay? I want 8 is included. So I want 8 and above. So I circled or boxed in 8 and above. So then I'm going to take off 7 and down. So I'm going to take off the accumulation of the bottom up to and including 7. So that's 1 minus the binomial CDF of 11.63, 7 and down, because I want 8. And the last one, we've got dribbling drummers, and there's a 48% chance we have a dribbling drummer. So we just do our standard deviation. Now it is out of 12 drummers drumming. So our N is known. So that's a set N. So then what do we have for our standard deviation? It is a formula right here. It's binomial because our set N. And so then we just do this standard deviation formula right here. And then you fill that in, and that's on average, or yeah, it's about 1.73 drummers as a standard deviation on average, as we took samples of 12 over and over and over again. All right, that is your 12 days of statistics. So I hope you did well on that so that you are getting a grasp of your probability.